Hello, everybody. I think we can start now. It's 4 p.m. Central European time. This is Ruggero Poletto from CFD FEA SERVICE, and I welcome you to this webinar, which is held together with Brian Klein from Thunderhead.
Hello.
Hi, Brian. Today, we are talking about FDS scalability in an HPC system. And by HPC system, I mean any system like your own computer. This webinar is broadcast via YouTube. You can interact with myself or Brian at any time. There is a chat on the right-hand side of the YouTube video. Just type over there the questions, and we try to reply to your questions live during the presentation itself. So don't be shy, just make questions. It's a good time for that. A brief presentation of CFD FEA SERVICE. We are an Italian company incorporated in 2018. Among the other service we do is a cloud HPC service, which has been recently connected with Piracy. So we work together with Thunderhead. The service, which is going to be illustrated also later on, is basically a cluster where you can run your own simulations. Given from this experience, about a few hundred simulations every day run on the cluster, I found that most of the time people have troubles reaching a good scalability. But what actually I mean by scalability? Scalability means an increased number of hardware resources, used to run a simulation. We expect to reduce the time of the required in order to get the results. For instance, if we run a simulation on 4 CPUs and we get the results in 1 hour, we expect that if we double the CPUs, so we use 8 CPUs, we get the results in half an hour. So we get in half the time the results. During this whole presentation, I try not to be too much technical, but there are a couple of magic words we need to focus on. In particular, the word CPU, which identifies a part of the hardware resources which is used by our software, FDS, in order to run the computation, so to run the simulation. And then there is the RAM, which is the memory available to the software in order to memorize all the information of the simulation, in particular the mesh and the geometry. There are a couple of definitions also which are very important. The first is the speed up. It means how much the simulation is faster, and it is always compared against the simulation time, the time to get the results performed with one single CPU. So the speed up is the ratio between the time required for the simulation to complete with one CPU and the time for the simulation to complete with n CPUs, where n keeps increasing. And then there is the efficiency, which is the speed up divided by n, so divided by the total number of CPU. This somehow gives us an idea on how much we are efficient in terms of reaching the scalability, in terms of increasing the number of CPUs, the number of hardware resources we use for that particular simulation, divided by the total time for those hardware resources to complete the simulation. As a general behavior, okay, as for the same problem, for the same simulation, as we increase the number of CPUs used, okay, at the beginning, we have a linear speed up. So as long as we multiply by 2 the total number of CPUs, also the speed up gets multiplied by 2. Okay, so it's a linear link between the two. But as we keep increasing the number of CPUs, this speed up will no more be linear. It tends to become flat. Okay, this means that as we keep increasing the number of CPUs, we are step by step reducing the efficiency of our speed up. And probably the real question we're going to answer during this presentation is, when are we reaching this limit? It's difficult to give a general, let's say, rule, okay, because it depends a lot on your setup, it depends a lot on the mesh size, it depends a lot on the models, but by the end of this presentation, we'll give you some simple guidelines that somehow allows us to remain in the linear part of the relation between the number of CPUs and the speed up. One of the things we just said is that this speed up to CPU to speed up graph obviously depends on the size of the problem. As we keep increasing the size of the problem, so we keep increasing the mesh size in particular of our problem, the linearity between the number of CPUs and the speed up tends to be higher, tends to extend more towards a higher number of CPUs, and so we reduce the moment in which we go to the flat place, so we reduce the efficiency of our speed up. We already have one first question. What is the maximum limit for FDS? Well, depends on what you mean by maximum limit, in the sense, if you mean by maximum limit of CPUs, there is not a real limit. It depends on your hardware resources, actually. If you mean maximum limit of the speed up, a linear relation between the CPU and the speed up, well, we need to pay attention to this presentation some more in order to get a reply to this question, okay? It's a long reply. Well, moving on, as we said before, as we increase the number of CPUs, at some point, the speed up won't be, the relation between the speed up and the number of CPUs won't be linear anymore. This means that we are decreasing the efficiency, okay? So the efficiency becomes negative, becomes lower than 1, and at some point, it could also be negative. This means that as we keep using more and more CPUs, we might at some point also take a longer time to get to a solution compared to a case with a lower number of CPUs involved. So in order now that we got this, let's say, theory part in place, we can have a closer look at the parallelization methods which we have available in FDS and in general. In fact, the hardware resources we have in place, we need to know them very well. We need to know very well the hardware resources we are using for our simulations, because there are some features of these hardware resources which can be used positively by FDS or negatively by FDS in terms to reach the scalability. The modern computers have two different types of approach in order to guarantee parallelization. One is called MultiCore, and the second one is called MultiThreads. They are different, and we are going to see how they are different. But in order for you to understand what type of hardware resources you have in your own computer, all you need to know is open the task manager, okay, go to the performance tab and check. There are a couple of lines over here. There is one which specifies cores, and 2 in this case. It means that this computer has 2 different cores, so the multi-core approach with 2 cores. And the second line tells you logical processors, 4. It means these are connected to the multi-threads approach. Modern computers, in particular Intel ones, they take advantage of both these approaches. AMD, the latest release of AMD processors are also taking use of both approaches, but it's let's say a news for AMD. Until let's say a couple of years ago, AMD was only had a multi-core approach. Well, these are features of any hardware. Okay, so your own computer has this feature. Okay, so we need to know very careful how our computer, what are the features of our computer, what are the resources we can use, And obviously, we also need to know that FDS can positively use both these approaches at the same time. So not just one or the other, but we can use both the approaches simultaneously. But what are the difference of the two approaches? In here, I had to put two small diagrams actually, and I try to explain the two approaches. So pay attention to these slides, which is quite important. In the multi-core approach, we have our problem, which is the simulation we want to perform. In multi-core approaches, our problem needs to be divided into sub-problems, okay? Each of which resolves part of the simulation, okay? Each of these sub-problems is assigned to one core only, okay? So each core resolves only a smaller problem, a smaller simulation than the ones we had at the beginning. So given this, each core is able to resolve a simulation faster compared to one core handling the whole simulation, okay? And at the end, when we get the results from all the cores, we can gather them out into one single place and get the final solution of the simulation. Okay, in MPI core, so we need to split the problem, assign this problem to one core, assign each part of the problem to one core, and then collect everything into one single solution. So keep in mind this, the splitting part, and then the recollection, so union at the end. In the multi-thread approach, is completely different approach to get a solution to the problem. We still have one single simulation here, but this time we're not splitting the simulation among several cores. We are allowing a certain number of threads to work simultaneously on the same simulation. Okay, so these threads somehow they are coordinated and they work into that very same simulation in order to get the results. In here, there is no a splitting phase and a reunion phase at the end. Okay, we just have threads which need to be coordinated in order to work together on the same simulation. I hope I made this part quite clear. I try to be as clear as possible, because these two different approaches obviously are important, and in order to understand the features of the two approaches, it's also important to know how they work. From now on, we are going to focus a little bit on the multi-core approach, which I remember, starting from one simulation, we need to split the simulation into smaller ones and assign these to one CPU usage. So how can I split the simulation in FDS? How can I tell FDS to divide the simulation into a certain number of smaller ones and assign these smaller problems to one single CPU? Well, everything relies on the mesh tag. In here, obviously, I'm showing you a simple mesh performed, let's say, written in an FDS file. In the first line refers to one single mesh, which is the simulation we want to solve. In order to split the problem, we need to manually split this mesh line into a certain number of sub-meshes, each of which is smaller than the ones we started from. The ones we started from had 10 cells in X, Y, and Z directions. Instead, these ones, which are, let's say, a portion of the beginning one, they only have 5 cells in each direction. And also the coordinates of the points X, Y, and Z, they are different compared to the starting one. Obviously, all of these summed together, okay, they are exactly equivalent to the starting one, okay, but they are divided, so they are like a problem divided into smaller ones. By assigning a mesh in this way, we are somehow telling FDS we want to solve one simulation, but we want to solve a certain number of sub-simulation in order to get the results for the bigger simulation we want to do. Another thing which is very important is that we can assign each of the mesh we have so divided to an MPI process, so to one of the core in particular, in which we want to run the simulation. Okay, this MPI process is just an integer index which starts from 0 and goes up to basically the number of cores we have available in our own computer. Okay, so the maximum number we need to know given the hardware resources we have available in our computer. Actually, the number of cores we have available in our computer -1. Using this MPI process, it is possible to, let's say, assign each mesh to one different cores, or in case to assign also multiple mesh to one single core. Okay, so in case I have 3 different meshes, like in this situation over here, okay, and these meshes, they have different size in terms of IJK, so in terms of number of cells, okay. In this situation, I made an example in which in the first line, I have 17,000 cells, and this number is calculated by 23 times 74 times 10, okay. And I have 2 more meshes, which are much smaller. One is about 5,000, and the last one is about 7,000 cells. I forgot to say that obviously the size of the sub-problems we are generating depends on the number of cells we are assigning to the mesh, okay? So somehow we need to split these meshes in order to be equivalent in terms of number of cells, of total number of cells. In this case, let's suppose we cannot split them anymore. I can use this MPI process tag in order to assign the first mesh to one processor and the second and the third mesh to another one. Okay, in this way, the total number of cells available that needs to be computed by the processor number 1 are 5,000 plus 6,700, which is a number much closer to 17,000 of the processor 0 than our initial situation. In this way, we saw also how we can somehow equilibrate the workload between the several processors. And this is an important operation to do, in particular if you want to reach good scalability. We need to make sure that every core has almost the same amount of workload compared to all the others. What happens is if this amount of workload is not, let's say, in equilibrium between the cores, well, the core which has a lower amount of workload, when it completes the simulation, just stands still and waits for all the other to get at the same point where it is, okay? So we have, let's say, a huge amount of workload which is lost in this way just because we have a core waiting for the others to catch up. A common situation, obviously now I'm making let's say a more realistic example in which we have about 8 meshes, eight different meshes, different both in terms of bounding box we are defining and also the total number of cells per each, let's say, mesh. So as you can see here, this is the initial situation, and in here I made this graph which shows per each core the number of cells which needs to be computed. As you can see, I have the core number 7, which has about 100,000 cells to compute, and instead there are many others like core number 1 or core number 2, which has only 25,000 cells, so a quarter of the total workload of processor 7. This means that I expect the processor 1, the core 1, to wait for processor 7 to finish at least for 3/4 of his time, of his computing time. This is a huge, let's say, waste of computing hardware resources when executing the simulation. What we can do, we can redistribute the meshes using this MPI process. In here, I assign the first line to MPI process 0, and the MPI process 0 as also the third one, and so on and so forth with all the other cores. And thanks to this redistribution, I managed to get a more, let's say, a greater equilibrium between the workload between the cores. As you can see now, they are almost all between 75,000 and 100,000 cells. So the workload gets very similar between all the cores. And this means that already this simulation performs better than the ones we saw before. So just by defining a good balance in the workload using this MPI process stack. Obviously, in a generic case, also the fact that some mesh are computing the fire while some other are not will have an impact on our scalability. But already, if we achieve an equilibrium in terms of number of cells to be computed by each CPU, okay, it's a good starting point for our scalability. Obviously, once we have completed the equilibrium between the processor, between the workload of the several cores, we can launch the simulation in a multi-core environment. How can we do that? Well, that is very simple. There is a command once we have installed the FDS, which is MPI exec -np, the number of core we want to use, FDS, and the file name.fds. Obviously, if you use PyroSim, you are not requested, let's say, to type this command, but this is a general presentation valid basically for anybody. So if you want to get, let's say, a deeper knowledge on this, it's possible to have a look. What I want to stress is the fact that FDS in the log files that provides us, it tells us how many cores it is actually using. There is this part which I highlighted over here. If you see, the first line says MPI enabled, number of MPI process equals to 4. It means that we are running the simulation on 4 different cores. It is obviously up to the user the verification that the number of MPI core we assign in the command, the number of MPI core we have available in our computer, and the number of MPI core we have assigned to balance the meshes, okay, there are somehow consistent between them. Okay, FDS does not check whether there are hardware resources available on the computer to be used, let's say, given the request made by the user. We have one question, which is the website for CFD. Well, we're going to see also later the Cloud HPC platform quickly. So over there, you will see the contact information and also the website. So far we talked about the MPI parallelization, which was the most complex one because it required the user to split the mesh. So it's a manual, let's say, management to be made manually by the user. We can also have a look at the multi-thread approach, which is by far easier. In order to execute a multi-thread approach, all we need to do is to set an environment variable in our system, which is OMP num threads, and this needs to be equal to the number of threads we want to use for the simulation. Keep in mind that in this moment, we don't need to split the mesh anymore, okay? Because in multi-thread approach, every thread they work together. Somehow they are coordinated into working on the same mesh. This approach doesn't require an intervention by the user, can be executed by typing one single problem, but according to my experience, it doesn't have a good scalability. In general, using more than 2 or 4 threads gives a low efficiency in terms of speed up efficiency. Okay, so I wouldn't recommend to use more than 2 or 4 threads during one simulation. And this forces us, in order to achieve a good scalability, to use the multi-core approach. Okay, so even if this is easier to set up, easier to implement, unluckily, it's less efficient than the MPI, the multi-core approach. That's why we needed to give this explanation. Obviously, as we said before, the two approaches, multi-core and multi-threads, can be also simultaneous, can work at the same time on the same simulation, okay? And in order to do that, we need to combine together, let's say, the initialization on FDS. So we need to both define the OMP non-threads in here, and also, instead of executing just FDS, we need to run FDS with MPI exec. When we launch FDS in this way, we are going to see, as we said also before, in the log provided by FDS, the use we made of MPI cores and MP threads. So FDS at any time tells us how many hardware resources we are using. Keep in mind that in a situation like this number of threads refers to the number of threads, not to the overall number of threads, but to the number of threads used by each single core. Okay, so overall, the number of CPUs we are using is the number of cores times the number of threads. There were a couple of questions. One is, what is the recommended maximum cells per single CPU? Well, I had a slide, which is this one, which replies to that question. Obviously, it's difficult to tell in general, but in a multi-core approach, we can go up to 10 or 20,000 cells per each core. Okay, going below these thresholds may reduce the scalability of your own simulation. For the number of threads, as I said before, I would suggest to have 4 at most, so not to have more than that. But at the same time, I always suggest to be aware of what are the hardware resources you have in your own computer. Like in my computer over here, I have 2 cores and 4 logical processes, which means 4 threads. Okay, so if I try to initialize a simulation with 4 cores in this situation, that would be a waste of resources, because I don't have 4 cores in order to run this simulation. I just have 2. So it's up to the user, the feature, not to use more core than the ones he has available.
Rajar, your audio cut when you were explaining the difference between cores and logical processors, at least for me. So if you might want to just really quickly highlight the difference between physical and logical, that'd be great.
So cores, they are what we said before as cores. Logical processors, they are actually the number of core multiplied by the number of threads. Okay, that is the overall number of logical processor. It's, let's say, a mix between the total number of cores and the total number of threads available in the machines. So in these machines, I have 2 cores. It means that I can use them, and I have 4 logical processors. It means that I can use either 2 core with 2 threads each, or in theory, I could also use 1 core with 4 threads. In both these situations, I am using all the resources available in this computer. Okay, if I allocate for one simulation, for instance, 2 core and 4 threads, I'm using altogether 2 times 4 means 8 logical processors, which are not available in this computer. The simulation will start regardless of this incorrect setup, but this does not match, let's say, the hardware resources available in the computer. There was another question. Too much of threads means slicing of domain. It increased the message passing data. You are absolutely right. Yeah. Actually, this is more right, in particular for the multi-core, okay, which also has this limit of 10 or 20,000 cells per single core. Oh, this is a lower limit. It's not the highest one. So we need to make sure that when the total number of cells we are assigned to each core is above this limit. okay, not below this. Another question that sometimes is made to me regards the RAM, so the memory available, whether that influences the simulation. The real question is not really. We just need to make sure that the RAM memory we have available in our machine is enough to handle the simulation, okay? So in here, we can see the graph over here. The used RAM is, let's say, the gray area, and the white one is the RAM still available, not in use. Well, as long as the situation is like this, it's okay, the simulation will perform. Having more RAM than, I mean, as long as we have free RAM, we don't need any more RAM in order to run the simulation. We won't benefit, we won't speed up the simulation anymore by allocating more RAM to the simulation.
And I just want to mention at that point that the kind of general rule for that is about 1.5 gigabytes per million cells. So it's a good way to estimate how much physical memory that FDS will require for the simulation. And if you don't have that amount of memory, FDS will still run, but it will start to put the memory allocation to your hard drive to swap space. And this is a very slow read-write process to go to your hard drive instead of staying in physical memory. So it will run, but it will be extremely slow if you overload the memory on your computer.
So in that situation, even if you correctly made all the other settings, okay, you won't ever reach a good scalability. Actually, you will be running, I don't know, very, very slow. As we said before, here in CFD FEA Service, we work together with Thunderhead because we provide a cloud HPC system. It is a cluster in which you can run your own simulation. Currently, it is also integrated directly within Pyrosim, if I'm correct, from version 2020.4. It is possible to execute, once you have generated the FDS file, it is possible to launch the simulation on the cloud and take advantage of the hardware resources available on the cloud. Consider that by cloud, the backend is provided by Google Cloud, so there is a huge amount of hardware resources available in order to run the simulation. How is the parallelization implemented in the cloud HPC platform? Well, it actually reads a lot, it actually catches a lot of information from the FDS file, which is uploaded into the platform, okay? The platform reads the number of meshes which are defined by the user, reads the number of MPI process, if there are any, and assign the total number of cores as the minimum between the total number of meshes written in the FDS file, the total number of MPI process, if they are present, and obviously the number of core available, which depends on the machine which is allocated by the user. Okay, so what is good over here is that any user can allocate for the time of the simulation a machine with a custom number of cores, which is like a good way in order to set up your own scalability. Given this small formula to calculate the number of core, the number of threads is calculated as the number of threads available divided by the number of core calculated just at the step before. Okay, so any hardware resources which is not used by the multi-core approach will be allocated to the multi-thread approach. Okay, this is how it is implemented into the cloud HPC. So what's nice is that the user doesn't really need to take care of the setup. It just needs to of the setup of the hardware. It just needs to take care of the setup within the FDS file in terms of meshes and in terms of assign the MPI process to the meshes, in particular to balance the workload as we saw before. There is a question, since there is a problem from transmitting Lagrangian particles between the subdomains, have you ever tested it? Well, let's put it this way, it depends on the problem. I didn't experience it. what I tested it is that there was a version, if I'm correct, correct me, Brian, if I'm wrong, there was the FDS version 6.7.0, which had a problem with the parallelization particles. I think that this has been solved in the most recent version. Currently in the platform, you can find any version up to the most recent one, which is 6.7.5. Yeah, a couple of more words about the platform, and then I'll leave the speech to Brian. Obviously, we have a high number of FDS versions, basically from version 6.7.0. We have all of them until the most recent one. We have the possibility for the user to, at runtime, decide what type of machines, how many CPUs to use. So this gives a great flexibility in terms of running also multiple simulations at the same time. Thanks to the cooperation with Thunderhead, currently it is implemented and integrated within PyroSim. So it is possible to launch the simulation from within PyroSim without actually opening the platform itself. At runtime, by accessing the website, it is possible, obviously, to see the FDS log as we are used to, but also to get an overview of the results. Any probe, which is, let's say, any device which is defined by the user, generates a CSV file, which is converted into a graph at runtime. So we have a continuous monitor of the simulation in order to know how the simulation is proceeding. In here, there are also information about how you can register, and for all the users, all the new users, there is, let's say, a good starting point, which is 300 virtual CPU hours, which are free and are very useful, in particular in the testing phase at the early stage to test the platform itself. I leave now the speech to Brian, which is illustrating actually PyroSim and how that works with the Cloud HPC platform.
Yeah, thank you very much. So we'll just do a quick overview here in the slide. I would also, I'll probably also share my screen and just do a little live demo showing how it works in two different models. And so, you know, just as a brief cover here, we released this integration with CFD FEA service back in the release 2020.4. 0902, which would have been September 2nd of 2020, where we had the UI integrated into the application. And so to get to that, in PyroSim, you go to the analysis menu, and if you look down the list a bit, you'll see Run FDS Cloud, and you'll also see an option for managing the cloud providers. And so what this means then is you choose, you know, the system is set up right now that we have one integration available. CFD FEA was very, very good at, to their benefit, they were super good at creating a very nice API and a very easy way for us to integrate PyroSim with their service. So all you need to do in PyroSim, and you can see this in the first dialog there, is put in the API key, which you get from your service account. So you would go to their service, set up your account. In your information, in your profile, you'll be given an API key. You take that and paste that into the dialog there. And then, and this is in the run cloud, so this is as you're running the job. Once you put in that API key, it's saved in PyroSim. You don't put this in every time. Once it's in there, it's saved. And then you would just select the FDS version that you would like to run, the number of CPUs, these are the virtual CPUs that were mentioned, and then what memory option that you want, which is essentially how many gigabytes of memory are allocated per virtual CPU. And that second choice, the memory option, that really is what determines the price that you're getting, because that changes the type of instance that you're being allocated and changes the cost a little bit. And all of that information is available on their website there. And then after you selected that, you just click OK, and then you'll see a run dialog similar to the second screenshot there, where it sets up everything in PyroSim, uploads the FDS input file and some associated PyroSim files, starts the service, actually reports back the simulation number or the ID for that simulation, gives you a reference there in the log to the hyperlink that you would follow to go monitor that simulation running. And then you can, at this point, close the window and actually shut down PyroSim, shut down your computer. You're completely free at that point because you've handed the computing job over to the cloud service, and you no longer need PyroSim even open at that point. There are some options at the bottom of the screen, or the bottom of the screenshot. You see we do add a hyperlink to make it easy to just click on and open up the simulation status page for that specific simulation right there through the UI. And then also there's a kill and a stop. And so we do integrate with the services hard shutdown, and also the graceful shutdown options that they provide through the API. So if you're like, oh, I didn't really want to do that and I don't care about the results, you can just kill it. If you would like to just shut it down at some point, you can click stop. You can also do these functions through the web application, so you don't need to use PyroSim to do this. This is just a helpful way to stop it if you need to directly in the UI there. Next slide, I think, where maybe this is where I'll screen share. Yeah, so let me, if I can, I'll take over screen sharing and I'll just go to the screen. And so now we should see here in a moment the screen update. So what I've done here is I did want to make a point about how you can assign FDS meshes to MPI processes. And in this, we have a tutorial on the website. I did post that in chat, but it's at our support website, and under tutorials, PyroSim, there's an FDS. Let me go into here. Right down here is, in the feature demo section, is assign FDS meshes to specific MPI processes. And through this tutorial, there's even an example file here, which I will show in a second, and then just explains how this works in PyroSim currently. It does use the run cluster option to demonstrate this, but this works. If I send this file to the cloud service, it works there too. You don't have to run cluster to make this happen, as it shows in the tutorial. So if I go into that example, this is the example file, and you can see we just have a series of meshes here. And if I go into the mesh dialog, you'll see for each mesh, on the advanced records tab, you set what process it belongs to with the MPI process variable and how many threads you want for that process. So you would just do this for each mesh and assign. You can see here now it's assigning to number 1. These two go to these two are to 2, and these two are to 3. So we're using 4 processes for 8 meshes, 2 processes per mesh. And then you can just run under the analysis menu, run cloud, and it should go. We have some plans to expand, to expand on this capability, where maybe we can list all of your running simulations, make it easy to maybe even view the data through a UI directly in PyroSim. But for now, you would just start the job and then go check on it. So I'm going to just shut this one down. And let me open up another example here. So this is one of the validation cases. This is the ATF corridors case in the FDS database of V&V simulations. And so now under the analysis, I can just go here to run cloud. I get a little warning about overriding. That's fine. And then here's my cloud simulation parameters. So part of the key, we made this intentionally shorter. There's more key characters here, but this makes it easy not to expose it if you save a screenshot or make a video or something. But you can, if this is blank, you can just click this button to create a new account. So if you need an API key, just click there. Right now, as I mentioned, we only have one provider. And then you pick your FDS version. This matches to the version that the software supports. So as the next release comes out supporting 6.7.5, this will default to the 6.7.5 version. We just want to make sure that PyroSim is building input files that are compatible with the version of FDS that you're running. But if you know that it's fine, you can also change. Eventually in the next release, you'll be able to change which version you want to run. Then you choose how many CPUs you want. In this case, we'll just say, we'll do 2, and then the memory options that we want here. And then I'll say OK. And the run dialog pops up here. So it's setting the run, uploading the file, starting the service, and the simulation is started. So it's very quick. You're just handing off the workload to the service. And now if I click on the simulation status link, it jumps right into the detail of the simulation, gives me all the information I need. It's pending, so this means that the instances are spinning up based on my request. You'll be able to see now it's running. I'm already starting to get some feedback from the simulation service, and you would just see your images below here for screenshots of your data, as was shown in the slideshow, and you'll be able to see your progress and monitor things from here. There are other ways through this service, so you can go to the storage. You can go, here's the output for that simulation that I just started. Here are the data files that were uploaded, and you'll see your output start streaming here. You can download these files from storage to your local computer, or look at specific files as it runs. So there's quite a bit of capability here just in getting your simulation results back down from the service. And so this is where you would monitor your simulations. You can also go to your just simulations list page and see, what jobs have started, what jobs are running, what's complete, and be able to just jump back and forth into that UI. So I think that demonstrates really the capability. Is quite simple from the PyroSim side. You have to take into account all of the advice that was provided about how to mesh up your model, how to assign those meshes to processes, make sure you have a well-balanced simulation, and you might even run some local simulations just to test out allocations. But then once you want to just hand all this work over and have it work on a faster service, or even a more scalable service that can far exceed the local hardware resources you have on your computer, then you can just chuck that file up into the service provider and go from there. So I'm actually going to send the kill command to that, and you can see that already the service is stopping. So it's a very direct connection. If I have that run dialog, you're communicating directly with your simulation on the surface. So I think I'll stop there and let you take back over with your slides and see if we have any questions. And I'm not hearing you. You're muted right now.
Yeah.
There you
go. Let's say the presentation is here. But I see that there are a couple of comments. CPU. There is one question from Nado. Are the virtual machine CPUs constrained to a 1-to-1 ratio with physical CPU? If not, then would it be correct that we would not achieve the same scalability as physical machine? There is a connection, let's say, which is basically 1-to-1 between the virtual machine and the physical CPU. Obviously, we need to be honest, at any time, there is the virtualization part, which reduces a little bit the performance. The hardware resources which is currently used is a ROM, EPIC ROM at processor, 3.1 gigahertz. So a very powerful processor. Consider that probably you lose a couple of percentage points of the processor efficiency due to the virtualization part. Anyway, it's a relatively small quota of, let's say, the total computing power which is available. I take advantage also to say thank you to all the people that took part to the beta testing of the project, in particular FSC Progetti and Argo SRL in Italy. But obviously I thank also Brian for the webinar and Thunderhead in general for working together last year in order to, let's say, integrate the two services together. In here, I put also the contacts of myself and the company in general. I didn't put, Brian, yours, but I think most of the people can refer to the Thunderhead website.
Yeah, that would be great.
There is another question. The virtual CPU will be more akin to threads or on a physical machine? Actually, let's say the ratio between threads and cores depends on the hardware infrastructure. The processor which is currently placed has a certain number of CPUs and the same number of a certain number of cores, sorry, and the number of threads per each core is 2. Okay. So I know this is, let's say, the infrastructure of the EPIC ROM, which we have in place right now. It can be different from processor to processor. So in case you have a specific question which does not regard the HPC, write us in private. Can you restart the job? Sorry. Yes. It's also a feature which has implemented right now. Once you submit the job, if there are .restart file, automatically, regardless whether you actually put restart equals to true in your FDS file, the simulation is considered a restart. Okay, so you will read the .restart file and start out with a restart. So yes, it is possible to do that. Obviously, you need to load not just the FDS file, but also the .restart file, which are produced by FDS.
And can you speak a little bit about I know you mentioned the CPU, but a little bit about the computing infrastructure behind the scenes, behind the service, what it's based on and what technology stack it's using?
One other question regarding the operating system. Currently, all the infrastructure works on Ubuntu. So any simulation will be performed on Ubuntu 16.04. Actually, this is transparent to the user in the sense that we just connect through a website, and so we can use it from, let's say, our operating system can be anyone, also on mobile. It doesn't need to be a computer at all. It will be implemented and will be released probably by the end of this month or the early March. A remote desktop into the instance in order to view the results directly on the cloud, also while the simulation is running. So with that, probably people will realize a little bit more of the fact that the infrastructure is based on Ubuntu. Currently, it's completely transparent. Is there another question by Salah? Is there any way to know whether the CPU used in hyperthreading is disabled or not? Ideally, when using MPI, you would want to use a physical core rather than logical. So is there any way to know that? It's a good question. It means that Salah knows the infrastructure or the hardware very well. The approach to the problem of the HPC infrastructure is of the fact that the user doesn't need really to care about aspects like this. Okay, so I can tell that hyperthreading is enabled. Okay, but is the let's say, as we saw before, it is the infrastructure itself that defines how many cores and how many threads to use. Okay, so it's not up to the user to, let's say, enable or disable this hyperthreading part. Is another question by Jess. Is there a way I can estimate the number of CPU hours of a simulation will take? This is a common question that I receive 100 times. It's very difficult for a general case because it doesn't just depend on the mesh size. It depends on the models we are applying. For instance, whether there is or not the radiative heat transfer. It depends on the type of simulation. It depends on several parameters. What I usually suggest is just to run the simulation for 1 hour or something like that, and see how many seconds of the simulation are performed, and then proportionally somebody can get an idea of the overall time of the simulation. Another question by Adil. I don't know if I can ask this, but thanks for the. We want to hear your plans on OpenFOAM GUI. Brian, so I leave this to you.
Okay, the short answer is we don't have any plans for an open foam GUI at this time. We are looking at different, I would say, like different opportunities to integrate more tooling into PyroSim, Pathfinder, maybe integrating them more. But at this time, open foam is a completely different animal. It would need a whole different application. There are other tool packages that try to wrap open foam in various ways, with green energy simulations and HVAC systems and all kinds of other things. So at this time, there's no intention of wrapping open foam or fire foam, to be more specific. But we are interested in that space. You know, we kind of try to keep up on progress for that tool set. I don't know very many people who use it in production, but I know that it's very popular in the research community right now. And there seems to be some growing interest, I'll say, over the last, it's been around for a long time. Fire foam has been in development for a while, at least 10 years, if not longer, that I've been aware of it. So, but as you know, as things change, if maybe that becomes the most popular tool, and it can keep up with FDS in terms of a practical simulation tool for engineering work for fire simulations, you know, we would certainly look into that more seriously. So, but we're always interested in new opportunities, and I think we have some opportunities to do some other things, and maybe even integrate these with the cloud computing service, like you know, having some kind of tool set to build lots of different versions of. You can use the Monte Carlo system in Pathfinder, for example, to build up hundreds or thousands of simulations to test variables. And we'd be able to just send up that batch of jobs to a cloud service like CFD FEA. Same thing with FDS. We're looking at ways of creating run sets or test matrices, and then being able to send all of those jobs up to work on testing all of the different variables for sensitivity analysis and things like this. So I think there's a lot of work to do still in this area. And maybe even integrating tools like CFast into the PyroSim UI, so that you can build quick zone models and maybe run those locally, or even send up large batches to be run on the cloud service. So I think there's still quite a bit of opportunity in this area to grow and to take advantage of, you know, services like this, both with PyroSim and directly. So hopefully that's helpful. Maybe not the answer people are hoping for. I know that there's a lot of excitement about open foam and fire foam in some communities in the world. So we'll just kind of keep our ear to that rail and see how things are going, and make some decisions. But at the moment, there's no development plans for that.
Yeah. Let me just add one thing. Since we were talking about scalability, and I know fire foam quite well as well.
Yeah.
Why I want to say this? Because very often the software needs to take care to have implemented the MultiCore and MultiThreads features. We saw FDS, which by coincidence had both this feature, but in OpenFOAM case, we just have the MultiCore approach. We don't have the MultiThread one, okay? So as we said before, the parallelization and the scalability really depends a lot on the software and on how that has been implemented, okay? So OpenFOAM does not take advantage of multi-thread approach, and it's a feature that somebody can have a multi-thread computer, but it cannot use it actually with OpenFOAM.
Okay, looks like we have all the questions covered so far. If there's anything else, I don't see anything else. If you do,
no. I think people are thanking us a lot, so we thank them as well. Okay. Yeah. I hope we spend a good 1 hour together. And what to say, Brian?
Yeah. So I would just say to wrap up, if you have questions about PyroSim and integration and how that works, reach out to support at thunderheadeng.com. You can just go to our website, Thunderhead. If you have questions more about the CFD FEA service, how it works, maybe other integrations, planned features, things like that, please reach out through their channel. You can see that on their website. And that, just to double check that, that's the website is cloudhpc.cloud is the easiest way to get to that. So you can start there. You can also click the link through Pyrosim if you have that in the Run Cloud option, and it'll jump you right in. So we look forward to hearing from anybody as they run this or test it. Any suggestions for new features, both on the Pyrosim side and the CFD FEA side, would be welcome. So.
Okay. So thank to Brian again.
Yeah, thank you.
Thank you for all the participants, and I hope to talk to you all soon. Bye.
Bye-bye.